Hi, hi everyone. I don't know if you met me before. I'm Ruba, and today I will introduce the topic of a novel approach of using discrete event simulation and heuristic method in productivity improvement in production system. So that's my research. So I'm a PhD student from UTS. My supervisor, Dr. Mickey Clemon, and my co-supervisor, Dr. Matthias. And yeah, so my research, let's take this off, particularly in using introducing a new approach about in the productivity improvement in the production system. So what's the production system? So for the people, yeah, just a quick introduction, that we have raw material and resource to transform this raw material to a product or service. So that's what we mean by production system. If we have demand and the transformation process is called the production system. So my research focusing on the high level, the management level. So how the management can optimize their production system to enhance the efficiency, reduce the total production time, so they reduce the cost, and be competitive in the market, the global market. So in the Industry 4.0, the product life cycle time is so short, so the company should respond to the changes quickly and optimize their production system. So the problem that I'm looking at is how to optimize the number of workers and how number of machines, the optimal number of machines, the best facility layout, and production scheduling. So these, of course, these problems, there's a many technical and optimization algorithm to solve these, but the idea is using discrete event simulation beside this algorithm, existing algorithm, it will be a beneficial. To prove that, we've applied approach, and we test the approach in different categories. So first, before we start with our approach, I would like to just explain how the theoretical, how the ways that to study any production system, the ways should go through. So the different process, for example, when we start with a system, some manufacturing company, they run the experiment with laser point. Okay, with experiment with this, start with this block, experiment with the actual system. They go to their production system, stop the production and make different changes. Maybe they can change number of workers and change number of machines, and they look what's happened to the output, how many parts we produced. But actually this case is not barely used. It's not popular because it's costly. If you want to change anything in the system and stop it, it will cost a lot. So most of the managers and decision makers go with experiment with a model system. So the experiment with the models, it could be a mathematical model, doing an equation, represent what's going in the site, in the real system, and solve it mathematically, and also by physical model. You know, physical model could be like a clay made of car, a car made of clay. It's a model, but in the operational research, it's different. For what we said with the physical model, it could be, for example, let's give a simple example. The restaurants have number of workers and they want to see the output if they move this way inside the aisles, and they saw how their productivity will be. The physical model will be not in the restaurant itself, people carrying parts and moving aside, and they doing the testing in the real people, but it's a physical model and say the performance is not in the actual production system. So in the mathematical model, we have two ways: analytical solution and simulation. And where's my approach start from this way, simulation, but it's combined with analytical solution. So what's the simulation and what's the analytical solution? Analytical solution is useful when the mathematical model is simple. For example, if you have a distance and the equation, the well-known equation that if you can compute the time if you have the distance and the velocity, so you can compute the exact solution and what's the time the part will be if you know the distance and you know the velocity. But in the natures, the equation is more harder and more complex. It's look like a matrix when the production system is get more complex. So the best solution is using simulation to monitor the behavior of the production system. So the simulation, it could be different type of simulation, but yeah. So as I said, I have my approach come with using combination of simulation and optimization. As I said, the simulation is better for stochastic behavior when we don't know how the system will behave. There's a randomness in the behavior and random in customer demand and transportation time, stochastic failure, the machine could be fair, and repairing time, all can be included in the simulation. In opposite to in contrast to the mathematical modeling, we can't capture these variables. And also in the dynamic complexity, when the production system is become more complex, it's for the managers, they can monitor as individual station, but it's hard to monitor the whole production facility. So the simulation here is the perfect tool to capture all these dynamicity and the stochastic behavior for the system. But however, the simulation by itself is not an optimization tool. It can use the simulation to test different improvement scenarios, different what if we change the number of workers, what will happen for the key performance indicator, but it doesn't give you an optimal solution. So the optimization method can help with achieving an optimal or near optimal configuration. So they will start with give a configuration that best possible value for the some performance indicators. So they like a starting point for your simulation. So as I mentioned, there's different kind of simulation, different type, depending on the problem. So we have a continuous simulation and Monte Carlo simulation and discrete event simulation. This is the one we will talk more about it. That's what I'm using. So just for curious, what's the continuous simulation and what's Monte Carlo simulation? So continuous simulation, it's this type of communication for a modeling system with random variable that change continuously over time. For example, if you bring metal and you monitoring the heating status, the heat distribution inside the metal, it's kind of simulating the temperature for this metal. So it could be like a bending or cutting or heating continuously over time, changing in the status of the events continuously. For Monte Carlo simulation, this is employee random sampling for addressing certain stochastic problems that do not evolve over time. So it's more for static systems. Also, an example is that when you roll a dice, two dice, and there's a probability, it gives you the probability of rolling the dice. It's a static system. But the discrete event simulation, here's what we are interested. It's modeling for random variable that change over time for dynamic system, but only in discrete manners. So, for example, that event occur, that status of the system change over time. There's a material enter the production system, departure, they capture all these events. All right. So, yeah. So someone will say why you are using combining discrete event simulation with a heuristic method. So why we don't combine discrete event simulation with exact methods? That's optimization method will give you an optimal solution. So the answer that when the complex system is become the system when it becomes more complex, the production size for the okay, add someone. So the production size will be increasing exponentially. So the mathematical problem will become so complex, and it's require a long time to solve. So we want an good solution, optimal or near optimal, with a feasible amount of time. So that's why we use heuristic methods. So it's faster. Heuristic or meta-heuristics, it's given a near optimal solution, and it's good to be combined with simulation. Example on these heuristic methods, such as genetic algorithm, particle swarm optimization, and colony optimization, table search, simulated annealing. So I put here a reference for if anyone interested in these heuristic algorithms, they can just go and find. But I've focused on genetic algorithms with discrete event simulation, also because it's the most popular in the literature, and prove its effectiveness in, when it's used combined to simulation. Also some heuristic, and actually it depends on the problem. So each problem we choose different optimization algorithm. Okay. So my research was focusing on three. My approach actually can be applicable for 3 areas. In the heavily manual production system, like a wool shearing shed. Also in the additive manufacturing, because it's have low volume and high mix products, and low mix and high volume product in assembly line productions. So this is the area that we apply our approach. Here, this is the wooling shed. It's I've been involved in the Australian Wool Innovation Automated Wool Handling projects, and we've built a digital model that represents the shearing sheds. So this is the simulation, like it's a digital model represent the real case. So here's the real case. We've tried to simulate different scenarios to find what's the best layout and what's the optimal processing time. We try to increase number of the equipment. So we have multiple shearers. They shear. There's a stochastic variable, like the processing time is vary from worker to another. So here's the benefit of simulation that can capture these variable in the processing time, and apply different improvement scenarios. So after they shear the fleece, they send it to the skirting table. This is called the skirting table. They put the wool, and they take the bad wool from the edges that include continents. And after that, they put it in the presser machine, then send it to the distribution, seal it, the bag, and send it. So we test different improvement scenario in the simulation. We test the linear layout. The blue blocks here represent the shearing stance. And here's the skirting table and the pressing, and this is depends on the wool type. It could be go to a different storage bin. So here's the two layout. So we just start testing different improvement scenarios. For example, here's the people. There's wool handlers carry the wool from the shearers and send it to the skirting table, and we can also the benefits of simulation. You can monitor the status of the machines, the workers, and on life. So you can see what's happened. What is the bottleneck station? We can identify the bottleneck. We can identify the efficiency of the workers, the utilization of this station, and so that's the benefit. So we've compared the layout, the linear layout, with the curve layout. That means if we have the shearers in the curve, how's the productivity will be, now the output. So we've as a result, after testing 3 different scenarios. First scenario, we was changing the number of workers that carry the wool because the skirting table was the bottleneck. So we've tried to increase number of workers and see how much the output will be. The other scenario was introduce another skirting table. The third scenario was reducing the skirting table processing time if we want to go through the automation. So what's the optimal processing time for the skirting table? So here we found that the curve layout can save 33 minutes saving because of course it will reduce the traveling distance for the workers. Adding another skirting table will increase the fleece from 826 till 856 fleece per day, so 3.5. Then increasing the number of wool handlers is not that much saving. It's only 0.8, so it's not feasible. It's not a good solution. And also reducing the processing time for the skirting is the highest percentage. It can increase 5% if we make the skirting table processing time 22 seconds only. So here we can analyze the production system with different scenario and see and monitor the production system, the output, for example, the throughput. Another scenario, another case study with in the additive manufacturing. Actually, in the additive manufacturing, this approach haven't applied before in the additive manufacturing. So it's the first application for the additive manufacturing, especially it's growing up now, and we've tried to solve scheduling problem and identification, bottleneck identification problem. So in this graph represent, like, if we have multiple printer and we have multiple unpacking station and multiple sandblasting process, it's the process of printing powder bed diffusion printer. So if we print how to assign the jobs to the machines in terms to minimize the mix span, the total production time. So we did a simulation model and we combined it with a genetic algorithm. So in the literature, the AM start shifting from producing prototype to direct production. So there is now the company trying to adopt additive manufacturing and 3D printer in the production of their products, and scheduling and production planning in AM still in early stages. And most of the published work is published in the last 4 years. So still in early stage. So the application of this approach, it will help a lot in the planning for increasing the size of the facility of additive manufacturing. So most of the research that have done in the additive manufacturing is nesting and scheduling problem. It's about how to use the optimization algorithm to put the parts inside the building units, so inside the printer, the orientation of the part, how to put the, because the orientation is very important, and if the put the orientation different, that affect the processing time. So most of the simulation about nesting and scheduling problem itself, not combined with identifying the status with different setup. And in the conventional manufacturing, they use discrete event simulation before with optimization tool for solving complex production problem, but it haven't been applied in the additive manufacturing. So here's the gap. So this is will be the first application for this approach in the additive manufacturing field. So our methods it's not about just scheduling. We are trying to facilitate resourcing, such as bottleneck identification. If we did a different setup, and according to this setup, we can identify which is the bottleneck station. What I mean by the bottleneck station, that the station that had a higher processing time, so it's work all the time, and the entities or the parts, it will be stores in front of this station because it cannot handle the work. So this is the bottleneck identification and facility resourcing. And then we do job scheduling optimization using genetic algorithm. Our goal is to reduce the max span, which is the total production time, Our results that we've tested, as I said before, we test different number of resource, like we change the number of workers, different setups, and changing number of printers, also, and unpacking station, number of sandblasting, number of buffer or building units that's where the parts built. So we measure the max span in different configurations, and we see if we have a 20 part or 100 part to produce in the additive manufacturing printer. So what's the max span to produce it? So we have here different max span. For example, we have 20 days to complete the jobs, but using the discrete event simulation, like we found, if we increase number of workers from 1 to 2, to drop the processing time from 20 to 14 days. So it's a big time savings, around it's around 6 days we save if we just increase only 1 workers. So here's we find that number of workers is the bottleneck here. If the production status need more workers, if we change the number of building units from 1 to 3, it's nothing happens. So it's not affecting the max span. If we notice after we analyze this status using when we use the genetic algorithm to optimize the schedule, optimize the sequence of job, which job should go first before the other jobs, we reduce the max span. For example, here we reduce it from in the same configuration. When we run the simulation model, it takes 12 days, but when we apply genetic algorithm, we save 4 days, still 3 days. So yeah, there's in the whole CTS, when we applied genetic algorithm combined with simulation, if we look at that with different setup, number of workers and different number of units, we can see there's always drop. This is the border with the border, always drop in the max span. So we always improve the max span when it's combined with genetic algorithms. So yeah, here's the facility resourcing. We've number of workers were the bottleneck to 30%, improvement in max span, changing in unpacking station from 1 to 2, just save 10%, sandblasting have less effect, it's changed 0.8%, but when it's combined with GA lead to 20% savings. So there's always improvement when it's combined with genetic algorithm. So here's the interesting part that the simulation can help you to run a huge number of experiments using, I've used technomatics plan simulation by Siemens. So there's a tool called Experiment Manager can help you to run for all the possibility and the combination of the setup. So we can run 2,462 with just less than 1 minute, 46.8 seconds. So yeah, the future work, it could be this huge data can be used for machine learning and develop. I've started working on that, so to develop a model to predict the max span in different setup. Yeah, this is all in the additive manufacturing. So in the assembly line balancing, where's the problem in the assembly line balancing? What's mean by assembly line balancing? When the assembly line balancing, that means you have to distribute the task between worker in even way. So the workload should be distributed equally to enhance the utilization of resource and enhance the productivity. And there's uneven, sometimes it will be, there's uneven work distribution, and that's due to changing in the demands. Some workstation have now should work more than because the demand is changing, or introduction of new products, unforeseen equipment malfunctions, breaking down the equipment. Also, inefficient management and process control. When the management give this worker more work than the other workers, or it's depends on distributing the task between workers. So it should be equal. So how we distribute the task is challenging to distribute the task between workers because each task is different when it's become a complex production system. So there's heuristic methods already built to assign tasks to station. So there's multiple heuristic methods such as KWC, too many heuristic methods, but I will go through it later. Just before we start, I wanna give an introduction about the literature and the research gap in the assembly line balancing. So this problem introduced for the first time in 1955. They suggest linear programming to solve this problem because it's an hard problem. It's not easy to solve. So then many scholars try to solve it under mathematically, heuristic, meta-heuristic, and simulation. But no one of them try to combine this simulation with a heuristic, like our approach together, to work together. Most of them, they use heuristic to solve the problem, like optimization algorithm to solve the problem, and then use simulation to evaluate the performance of this heuristic. But they don't use it alongside each other to optimize the productions, to optimize the assembly line. So also many scholars, many researchers try to use different heuristic methods separately and say which one performed best, and do a comparison or combine two of them together, combined with another meta-heuristic. So this is the first application for using heuristic with discrete event simulation as a supporting tool, as not as an evaluating tool for assembly line. For example, ONAL proposed heuristic for line balancing with simulation to test its effectiveness, but using discrete event simulation as an evaluation tool. So our approach was different. So our method is starting with the initial heuristic methods. Take a solution, take this solution from heuristic and use the output as an input for the simulation model. Then evaluate evaluating the performance of heuristic, and also create a new improvement scenario, not only the heuristic, and compare if it's satisfied with a good solution, we implement the solution. If not, we can go back, adjust the heuristic with integration with the discrete event simulation, and find different solution. So one of the discrete event simulation model that we built, for example, here this is assembly line. There's different parts coming from different station. There's a worker carry the part, go to the other station and do assembly. So yeah, so we test this. We've tested the simulation with different with the heuristic. So the first step in the heuristic, like computing, for example, this is a assembly line for building assembly products, and it goes through different steps from A to J. Each step represents a task. So we measure the predecessor, which is this task for loading the part. It doesn't need any predecessor. For screwing, 4 screws, it needs loading the part before it starts screwing. So here is the task and the average task time. So yeah, so here's the task data collection for the task for the assembly, for one assembly line, one assembly production line. So we use this data to build a heuristic method how to assign tasks to station. For example, we have 6 stations using heuristic method, and they assign task A on station 1, task G, B, C go to station 2, and the dark bold box represent the station. Task D go to station 3, and so on. So we are using the heuristic method. They said, for example, the task with a less processing time should go first, and this is the way how they compute the heuristic method. We run a simulation model on the right, discrete event simulation. Beside the heuristic method, we take the solution, how they assign tasks. For example, this station 2 take this task, and we run the insert this input to our simulation model and see what's the output. For example, they have to produce 400 parts if they follow this heuristic. So we build the model, evaluate the model, that make sure that our model represents the real case. It's not 100%, but very close, as much as possible. So yeah, so we found at the initial result, like current state before the optimization, before anything, that the throughput 288 parts per day. And if we have 4 workers, they have 4 workers. But if we have a heuristic method, we can assign the task. To reach the demand, we need 6 workers. And the utilization for the workers and machine is 76%, the average utilization. So we use discrete event simulation and start integrating the discrete event simulation with a heuristic method with different scenarios, scenario 1, scenario 2, scenario 3. So scenario 1 is just discrete event simulation, scenario 2 combination discrete event simulation with a heuristic method, and scenario 3, for example, discrete event simulation only. So if we look at this graph, the column graph, we can see that the highest efficiency is 90% when the solution integrated with discrete event simulation and heuristic method. And we've prepared a paper and will be submitted soon on that. And we published a paper in the Wool Automated and the Wool Innovation Project. You can find it. It's open source. And yeah, that's all. Thank you for listening. If anyone have a question, most welcome just to raise it now. I hope we finish on time. It didn't take longer, so we will have time for questions. Thank you.
A sort of question. I don't know if you mentioned that you were accounting for uncertainty in your, or rather discrepancy in your simulated model versus like the real world. Or perhaps when you get to that stage.
Yeah.
So do you plan to like account for that or somehow compensate for that in your simulation?
Uncertainty.
Uncertainty, or even like just the discrepancy in your simulation model, right? Because it's never going to very like 100% accurately model the real world, right?
You mean the Wool project, the first one?
Yeah, or even moving on, when you're going to apply this to manufacturing. So manufacturing application.
Yeah, actually, the model doesn't represent. It's represent. We validate that we capture some stochastic nature, like the failure and the traveling distance, and it's a variable. So it's a random variable. We capture these, and we tried our model. We compare it with the real production system, and the production. It was about the difference between the real production system and our computerized model, simulation model, is not that much different. So it was, yeah, pretty close to the real state.
Okay, so you're relying on a very accurate.
Yeah, the model
is. Model.
Yeah, the model is representing accurately for because we capture the data, we collect the data manually. We went to the shearing shed, we record the data, and we build the model according to that real processing data.
Great.
Thanks. Anyone else?
I guess I'll ask another question. So when you say you adjust the heuristic, so you sort of have like that feedback loop, what does that mean exactly? How you sort of like, what does it mean to change the heuristic, I guess, to improve the estimation?
Yeah, so we can integrate. It is a good question because we use the heuristic. Heuristic tell us to assign these tasks to station. So when we take the output of this heuristic and go to the simulation model and apply it, we can find bottleneck. So in the heuristic, we can't. It doesn't give you that indication. If you change these, it will affect the other station. It could make it other station bottleneck. So when we do the simulation, we can discover that. So the simulation ability is to give you a way to reduce the bottleneck. So if we do something to change in the heuristic, so we take this solution and change, update it. So you update the heuristic. So we give not optimal, it's a better solution.
Would you, I mean, are you coming up with a completely different heuristic, or like, are you changing the weighting? I'm just wondering what that means to like change.
Yeah, no, actually, it's not creating a new heuristic. It's still heuristic. Yeah, but it's sometimes because I've applied, the heuristic simulation, heuristic give me a good solution, but when I change it, use discrete event simulation, sometimes it doesn't give me the better solution. It sometimes go to your, as I said, it's depend when you change the heuristic. Don't change the heuristic. You can take the solution from heuristic, change it, and give you the base. The heuristic give you the base, and when you change it, you can get a better solution. So you can improve the performance of the heuristic if you update it with the discrete event simulation. This is the idea when we combine it with discrete.
I think Mickey's yeah. So you have some some discrete set of heuristics, and you just pick from those essentially.
Yes.
Yeah. Okay. That was more what I was kind of asking. Yeah.
Yeah.
Okay. Yeah.
Thanks for the question.
Hi, Ruba.
Hi, Fikri.
Thank you for the presentation. I just want to know for myself, for the to model your system, which software tool did you use?
For what?
Can you hear me? To model your system?
Okay.
Which software tool did you use for the simulation and for the analytical solution part? Yeah,
we used Technomatics Plan Simulation by Simmons. I can type it in the chat. Yeah, the benefit of using this simulation, provide you with a great analytical tool beside the simulation. So that's why we chose it. That's all for today's seminar. If anyone just have any question, just after the meeting, after this workshop, just can send it to me and I'm happy to discuss. Thank you. Thanks, everyone.